I hope that you all are safe at your premises. During these days, e-resources are of great help to communicate with each other. For the benefit of students and faculty, our college has started a series of webinars. Today, Department of Physics has organized a two-day national workshop on nanomaterials and its application for human and environment. A.S. College Kanna came into existence in 1946 and it is affiliated to Punjab University Chandigarh. The college has received A plus grade in its first cycle of NAC accreditation and A grade with CGPA 3.51 in its second cycle of NAC accreditation. Besides career-oriented add-on courses, certificate, diploma, and BBO courses, the college offers graduation and post-graduation in all the subjects like computer science, science, and commerce. Now, nanotechnology is an emerging field in the area of science and technology. For the detailed discussion on this topic, we are having with us Dr. Dhaliwal, President of Punjab University, Patiala. Dr. Karamjit has 12 years teaching experience and 16 years of research experience. In 2008, he has received Young Scientist Award by Punjab Academy of Sciences. He has made significant contribution in the field of nanotechnology, material science, and laser spectroscopy. He has published more than 60 research papers in international journals and has presented many research papers in national and international conferences. He has written 2 books. Dr. Karamjit has completed 3 research projects funded by UGC and DST. Presently, he is working on a research project of rupees 50 lakh funded by ISRO. He has guided 7 PhD students and 1 MPhil student. Dr. Karamjit has been a member of various professional bodies and organizations. Thank you, sir, for joining us. Now I request Dr. Karamjit Singh to share his views with us. Thank you, sir.
Good morning, everyone. Thank you, Dr. Manish, for such a
Thank you, sir.
nice introduction. It is my great pleasure that organizers has provided me such a wonderful platform to interact with the academicians and researchers. The topic of my today's presentation is fundamentals of nanotechnology. So, Dr. Manish, kindly allow me to share the screen. Yeah, okay.
You can start, sir.
Yeah. Okay. So, topic of my today's talk is fundamentals of nanotechnology. In this talk, we shall discuss first of all about the introduction to the nanoscience and nanotechnology, followed by the history of the nanotechnology. Then we will discuss about the synthesis of nanomaterials, followed by the characterization of the nanomaterials. If time permits, we shall also discuss about the few applications of nanotechnology. Nanotechnology is a multidisciplinary technology of the 21st century. It is assumed that nanoscience and nanotechnology will radically transform the world and the people of 21st century with the next generation industrial revolution. Functional engineering on molecular scale will be used to develop smart materials. Nanosciences, nanocomputers, and nanomachines embedded in new generation smart materials will revolutionize every aspect of human life. So if we look on the history of the technological advancements, it has been seen that basic advancements in science and technology come about twice a century and lead to massive wealth creation. In the previous 19th century, there was the revolution in the textile, followed by the railroad revolution. In the 20th century, in the first half, there was the revolution in the automobile sector, and in the second half, there was the revolution in the computer technology. Today, we are living in the era of the information technology that is possible due to the revolution in the computer technology. So it has been seen that every technology is having 3 phases. First phase is the introduction of technology. Second phase is the widespread adoption of that technology. And third phase is the end of rapid growth phase. So this computer technology was introduced during 1939 to 1969. So it was the introductory period of this technology. After that, there was the widespread adoption of this technology. So due to that adoption, of the computer technology in the society. Today we are living in the era of the information technology. So every technology has almost 25 to 30 years introduction period. So this is time is the introduction period of the nanotechnology. So it is assumed that after 2025, there will be the widespread adoption of technology, nanotechnology, which is a multidisciplinary technology in the society. It will be intermingling of the various disciplines of science and technology, and it will be giving us very beautiful and smart materials, which will revolutionize every aspect of life in the 21st century. So if we think about the need of nanotechnology, what is the need of nanotechnology? If we take an example from the present era of information technology gadgets are using the integrated circuits in which we are using the transistors. So the first transistor which was developed in Bell Labs in 1947, that transistor was having dimensions on centimeter scale. So the first generation computers, which were developed in 50s, 40s, 50s, those were also having very huge size. I have a picture with me. In that picture, I have seen a 5 MB memory, which was a very huge memory that was loaded by 4 or 5 persons in a truck. But today, we are having very compact, very smart sticks in our pockets, in which we can easily store data of the terabytes. So today, we are having very smart computers, compact computers. We are having laptops, palm tops, tabletops. So basically, if we have the example of the transistor, so a transistor which was developed in 1947, which was on the centimeter dimensions, today we are having million of transistors in a chip on the centimeter scale. So basically, the miniaturization in the electronic gadgets take place as per the Moore's idea. In 60s, Moore given the idea that after every 18 months, the number of the transistors on the chip will be doubled. In other words, we can say, he said that after every 18 months, the size of the transistor will become half. So electronic industry is following the Moore's idea since 60s, and the miniaturization is taking place. But now, if we need further miniaturization in the computers, in the mobiles, if we need more smart devices, more efficient devices, so we have to opt the nanotechnology. Today, people are talking about the molecular computers. Today, people are talking about the biological memories, which are very, very smart and very efficient. So it has been seen that the molecular computers, as well as the quantum computers, people are also talking about the quantum computers. So the quantum computers will be number of times, 100 times to you can say 1,000 times faster than the existing computers. Those will be very, very small in comparison to the existing computers. So biological memory will be having very huge data storage capacity. It has been seen that the DNA-based memories, which our scientists are trying to develop, those can store the data of the whole, you can say, computers lying on this earth. The data of all the libraries can be stored in a button-sized memory. So this is the beauty of nanotechnology. So if we have to talk about the introduction definition of the nanotechnology, as you know that basically technology is the implementation of the scientific ideas. Science is the mother of technology. So when we have to talk about the nanotechnology, we should also discuss a little bit about the nanoscience. So nanoscience basically refers to the world which works on the atomic or molecular scale from 1 to 100 nanometers. So basically, you know that a meter, we are talking about the meter, basically we will be measuring the length. So nanometer is billionth of a meter. Roughly, 2.5 nanometer. Diameter of the human ear is approximately on micrometer. on the scale. Here is cells size, weight, ultimate proteins is in our body in which systems proteins are playing very important role. So all the proteins basically are having size on the you can nanometer. Proteins are fabricated amino acids. Amino acids are having size on the sub-nanoscale. Just wait a minute. I think screen is now not shared. So basically, proteins are having the size on the nanometer scale. Viruses are mostly having size on nanometer scale. So in that way, you can say that nanomaterials are very, very smart and small materials. Basically, when we shall be talking about the nanomaterials, we will be saying that that material should have at least one dimension on nanometer scale. So here, when we are talking about the nanoscale, so that scale will be considered between 1 to 200 nanometers. Now, you may have query that why only 1 to 100 nanometer? So basically, all the materials are having some characteristic lengths because all the materials are having different properties. So those properties will be having some characteristic lengths. So if the size of the material will become comparable to that characteristic length, so the material property will become size tunable. So for all the materials, for all the properties, all those characteristic lengths are lying between 1 to 100 nanometer. So due to that reason, we are saying that nanotechnology is the technology of the materials which are having at least one dimension on nanometer scale. So when we have to talk about the definition of the nanotechnology, so nanotechnology is a field of applied science and technology whose theme is the control of size of matter and the fabrication of devices or materials on the atomic and molecular scales, generally between 1 to 100 nanometers. In other words, it is a design, characterization, production, and application of structures, devices, and systems with controlling shape and size at nanometer scale. In other words, we can say nanotechnology literally means any technology performed on a nanoscale that has applications, real applications. So basically, in layman language, we can say nanotechnology is nothing. It is just the application. It is just the production and characterization of nanomaterials. So what are nanomaterials? We have discussed that the nanomaterials are those materials which will be having at least one dimension on nanometer scale. So for example, you are having a thin film. If the thickness of that film will be on the nanometer scale, lying between 1 to 100 nanometers, so that film will be known as the nanofilm. If you will be having, for example, a wire or a rod, if the diameter of that rod or wire will be on the nanometer scale, so that will be a nanowire. Otherwise, that will be a conventional bulk wire. If you will be having the particles, if all the three dimensions of that particle means that, for example, if you are having a spherical particle, if the diameter of that particle will be on the nanometer scale, so that particle will be named as the nanoparticle. So if we look on the introduction philosophy, so old philosophy of creating things was to start with something big and make it smaller. Nanoscience generally starts with something atomic and builds things with it. So when we have to fabricate the nanomaterials, basically most of the researchers are starting from the atomic scale and builds on the nanomaterials. But it is also possible in the nanotechnology, later on we will discuss that we can also start with the larger materials, which are known as the bulk materials. For a nanoscientist, the material which is having no, you can say, dimension on the nanoscale, that material is known as the bulk material. So by starting with the bulk materials, we can also fabricate the nanomaterials. But most of the techniques, preferable techniques, you can say, are starting from the atomic scale. So in words of Nobel laureate Horst Sommer, we can say nanotechnology has given us the tools to play with the ultimate toy box of nature, atoms and molecules. Everything is made from it. The possibility to create new things appear limitless. Because nanotechnology has given us the tools to play with the atoms and molecules. Later on, we will discuss that in the nanotechnology, we are having the, you can say, instruments, we are having the scanning probe microscopes. with the help of those microscopes, we can visualize the atoms and we can pick and manipulate the arrangement of the atoms. So in that way, we can play with the atoms. When we will be changing the arrangement of the atoms, we will be having very, you can say, new as well as beautiful materials, smart materials. So if we look on the history of the nanotechnology, so nanotechnology is not new. Although the researchers started working on this technology intentionally in 80s, but nanotechnology is existing since the existence of universe. Because even if we take the example of our planet, when the planet was forming, atoms combined together to form the, you can say, molecules, to form the gases, then those gases were condensing to form our planet. Even the biological growth is also taking place due to the nanomaterials, due to the nanophase. So if we look on the things, man-made things, which are having the presence of the nanomaterials, those are also existing since centuries, hundreds of centuries. So since last 1,000 years. So in the Roman period, from 30 BC to 640 AD, people were using the nanomaterials to make the glasses. So there is a famous artifact residing in the British Museum in London. Its color changes from green when illuminated from the outside to red when illuminated from within. So basically, this beautiful structure is due to the presence of the embedded nanostructures. Similarly, the old church windows are also having very beautiful pictures. Those are also possible due to the embedded nanostructures, matter nanoparticles, which are giving us very beautiful colors. In the 19th century, in the first half of the 19th century, there was the invention of the photography. So in 1827, photography was invented. Photography is an early example of nanotechnology, which depends on production of silver nanoparticles sensitive to light. Light decomposes the silver halides to form silver nanoparticles, which are the pixels of photographic image. Similarly, in 1857, Michael Faraday discovered first metallic colloids, gold colloids. Those were also having the nanoparticles. Those colloids were having very beautiful colors due to the change in the particle size of the gold nanoparticles. On December 29, 1959, Richard Feynman delivered a lecture in America. The title of that lecture was "There is a Plenty of Room at the Bottom." In this speech, he stated, I want to talk about the manipulation and control of things on a small scale. He mentioned that if we will be having the capability to manipulate the material on the atomic and molecular scale, we will be having the new possibilities in material science, in science and technology. Although the nanomaterials are existing in this universe since the existence, since the formation of this universe, but the nanotechnology, the term nanotechnology was first time used by Japanese scientist Nori Taniguchi. He used this word to refer to production technology to get the extra high accuracy and ultra fine dimensions. In 1979, Rick Drexler used this term nanotechnology in his MTech thesis. But the research work started in nanotechnology in 1981 with the invention of a scanning tunneling microscope. So this scanning tunneling microscope is responsible for the development in the field of nanoscience and technology, because with the help of the scanning tunneling microscope, we can see the individual atoms, we can manipulate the arrangement of the atoms. So in 1981, first time, the quantum dots of zinc sulfide were synthesized. After the invention of scanning tunneling microscope, same group in 1985 invented the atomic force microscope. So these two microscopes revolutionized the research in the field of nanoscience and technology. Although the electron microscopes were existing before 50s, but those were not having the capability to manipulate the materials, manipulate the atoms. So these two microscopes were having the capability to manipulate the materials on the atomic scale. So with the invention of these microscopes, the work in the nanotechnology started. The first book in this field was written by Drexler in 1986. So the title of that book was The Engines of Creation, the Coming Era of Nanotechnology. In 1985, researchers discovered a very beautiful, very rugged, very capable material, C60. It was the molecule of carbon which was containing 60 atoms. So it is also known as the fullerene, buckyballs. This molecule is extremely rugged, capable of surviving collisions with metals and other materials at speeds higher than 20,000 miles per hour. Today, researchers are using these fullerenes, even the carbon nanostructures in the form of the carbon nanotubes, as the reinforcement agents in various type of the composites to enhance the strength of those composites. So these materials are used at very large scale in the automobile sector, in other industrial fields. Today we can fabricate any type of the structure on nanoscale. We can fabricate nanorings, nanosprings, nanotubes, nanowires, nanospheres, nanocubes, nanocoms. Any type of structure can be developed on nanoscale. Today we are having the capabilities to synthesize different type of structures. When we are talking about the nanostructures, there is an important term which is known as morphology. Morphology means size and shape. So nanomaterials are having morphology tunable properties, means the property of the nanomaterials can be tuned with size and shape. So morphology is a beautiful term in nanotechnology. So different morphologies of nanostructures can be easily synthesized using the various synthesis techniques. So now we are talking about the nanomaterials. As I have told you that nanomaterials are having smart properties. These are having the morphology tunable properties. So basically what will be happening when we will be going to the nanoscale? So it has been seen that the material property will be drastically changing. Here you can have the example of the gold. So the bulk gold means that gold which is not having the particles on nanometer scale. So bulk gold is yellow in color, that is inert. But if the size of the gold nanoparticles will be reduced to 100 nanometer, so that gold will be having the blue color and that will be having low reactivity. Previously it was inert on bulk scale, but when the size was reduced to 100 nanometer, its color changes from golden to blue and it becomes a little bit reactive. But when the particle size will be reduced to 30 nanometer, so the color of the gold will be becoming reddish and it will be showing the catalytic reactive properties, you can say, the reactive properties. So in that way, you can say that the physical appearance of the material is changing. So in today's era of fashion, you can say technology, if you have to wear different color dresses, so you can also have the different color gold ornaments. It is the beauty of nanotechnology. So now the question arises, what extraordinary at nanoscale? So it is the beauty of the nanotechnology that the physical, chemical, optical, mechanical, magnetic, all material properties drastically change on nanoscale. These properties become size tunable. Why? This is happening due to the following 5 reasons. First is surface to volume ratio increases with the decrease in particle size on nanoscale. Second is the confinement of electron-hole pairs, which is also known as quantum confinement. This term is commonly used in case of the semiconductors. Dominance of electromagnetic forces come into play on nanoscale. Importance of quantum mechanical models. Because here we will be dealing with the atoms and molecules very near to the atomic scale we are working. So here the quantum mechanical models will be applicable. Random molecular motions will be having importance. So due to these reasons, it has been seen that the nanomaterials are having side tunable properties, very beautiful properties. So how the surface to volume ratio will be enhancing? In this figure, you can see if you are having a 5 nanometer size particle, so these spheres are the atoms. So in this 5 nanometer size particle, 45% of the total atoms are lying on the surface. If we go on decreasing the particle size, for example, from 5 nanometer to 1 nanometer, so in 1 nanometer size particle, 92% of the total atoms are lying on the surface. As with the decrease in the particle size, number of the atoms available on surface will go on increasing. So the melting point of the material will go on changing, chemical reactivity of the material will go on changing, optical behavior of the material will go on changing. So you can say the material properties will go on changing with the decrease in the particle size. Similarly, you can talk about the electronic structure. In physics, people are commonly talking about the metals, semiconductors, insulators. So in case of metals, you know there is no band gap. In case of semiconductors, you know that there is a band gap. But if we will be go on reducing the size of a semiconductor, we go to the nanoscale. So it has been seen that that semiconductor will not be having the bands. That semiconductor will be having the discrete levels. So basically, here we are seeing that this is the, you can say, band structure, but here we will be having the discrete levels. Here we will not be talking about the band edges. We will be talking about the highest occupied molecular orbital HOMO and the lowest unoccupied molecular orbital LUMO. Here we were talking about the conduction and the valence band edges. So bands will not be existing no more on nanoscale. In that way, you can say that the band gap will be broadening and the band gap will be changing to the discrete levels on the nanoscale. So in that way, due to the band gap broadening, due to the enhanced surface to volume ratio, along with the other, you can say, material parameters, nanomaterials are having very beautiful side tunable properties. As I was telling you that we are talking about the nanomaterials which are having dimensions on 1 to 100 nanometer, because I was telling you that basically every property is having some characteristic length. For example, you may have studied about the coherence length, you may have studied about the exciton-Bohr radius. All these type of characteristic lengths are lying on the nanoscale. So when we are talking about the nanomaterials, nanomaterials can be of various types. Nanomaterials can be in the form of the powders. In nanopowders, we can have the nanospheres, nanocube, we can have the nanowires, we can have the nanorods, we can have the nanotubes. Nanomaterials can be in the form of the films, nanofilms. Nanomaterials can be in the form of the embedded structures, as we were having the example of the glasses, beautiful glasses. In those beautiful glasses, nanostructures are embedded. Nanophase materials can be there. Materials can be in the form of the membranes. Big membrane having the pore size on the nanometer scale. Those are known as the nanoporous materials. So nanomaterials can be of various types: nanopowders, nanofilms, nanophase materials, nanoporous materials. But most of the researchers are dealing with the nanopowders. So when we are talking about the nanopowders, so we are saying that the particle size will be lying between 1 to 100 nanometer in that powder. So we are also talking about some specific names which are known as the quantum nanostructures. We are talking about the quantum dots, we are talking about the quantum wires, quantum wells. So we have to understand here what are the quantum wells. We were discussing that a film, thin film, which will be having thickness on nanometer scale, 1 to 100 nanometer. So that film is known as nanofilm. That film will be named as quantum well if the thickness of that film, for example, that film is made up of a semiconductor material. So if the thickness of that film becomes comparable to the exciton-Bohr radius of the material, so that film will be named as quantum well. So every quantum well will be nanofilm, but every nanofilm cannot be named as quantum well. We will discuss later on what is exciton-Bohr radius. Similarly, we can talk about the nanowires. A nanowire is that wire which is having a diameter on the nanometer scale lying between 1 to 100 nanometer. But the quantum wire is that wire which will be having diameter comparable to the exciton Bohr radius of the material. So every quantum wire is nanowire, but every nanowire cannot be named as the quantum wire. Similarly, here we shall be talking about the quantum dots. So quantum dots are those particles which are having all the three dimensions comparable to the exciton Bohr radius of the material. So quantum dots are the nanoparticles, but every nanoparticle cannot be named as the quantum dot. So saying that these are known as quantum, and these structures are having the confinement of the excitons. So we were using here the term exciton Bohr radius. What is the exciton Bohr radius? In case of the semiconductors, we are having excitons. What is exciton? Exciton is a bound electron hole pair. So the size of that exciton is defined as exciton Bohr radius. So the exciton Bohr radius is the average separation between the electron and hole of that exciton. So for every material, that exciton Bohr radius will be different. So for every material, the size of the quantum nanostructure will be different. So as we were saying that quantum bells are those structures which are having one dimension thickness, you can say, comparable to the brains. Quantum radius of the material. So when the size of the Bohr exciton will be equal to the thickness of the quantum, so the item will be able to move along that dimension. To that region, quantum is known as two-dimensional structure. Quantum two dimensions structure will be comparable to the exciton Bohr radius, size of the exciton. So the exciton will be unable to move along those two dimensions. Exciton can move only in one dimension along the length. So that is the structure known as the one-dimensional structure, quantum wire. So in quantum dot, all the three dimensions will be comparable to the Bohr exciton radius. So the exciton will be unable to move in any dimension. So those structures are known as the zero-dimensional structures. So when we will be reducing the size from bulk to nanometer scale to the quantum structures, so the band gap will be changing, the density of states will also be changing. So here this material is a bulk material. I have told you that the bulk material is that material which will be having no dimension on nanometer scale. So in this, density of states will be continuum. So but when we will be reducing the size, for example, we are fabricating the films. So for example, we are cutting this piece to the small slices. We are fabricating the quantum wells. So the, you can say, density of states will be step-like. But when we will be further cutting this to form the nano, you can say, wires, quantum wires. So this step-like will be changing to this quasi-discrete function. So when we will be having the quantum dots, we will be having a discrete, you can say, density of states, delta function like density of states. So in that way, we can say that nanostructure are of four types: zero-dimensional structures, one-dimensional structures, two-dimensional structures, and three-dimensional structures. Known as three-dimensional structures. So when the excitons are confined in the particle, so I was telling you that for different materials, exciton Bohr radius is different. So for example, in case of the silicon, exciton Bohr radius is approximately 4.9 nanometer. In case of the gallium arsenide, it is approximately 14 nanometer. In case of cadmium sulfide, it is approximately nanometer. It will be approximately 70 nanometer. So for different materials, the value of the exciton Bohr radius will be different. So it is the characteristic length for the optical properties. So as the characteristic length for different materials for the optical property is different, so the quantum confinement effect in different materials will be coming at different sizes. So from you can say this slide, you can understand that why we are talking about the size should lie between 1 to 100 nanometer, because here the characteristic length for the optical property, the exciton bow radius. So this exciton bow radius is having different values lying between 1 to 100 nanometer. Nanotechnology is a multidisciplinary technology. It is the intermingling of physics, life sciences, chemistry, engineering. So mixing of the ideas from different branches of science is giving us the new type of the nanomaterials. So now how we can synthesize nanomaterials? To synthesize nanomaterials, there are the two approaches. One is known as the bottom-up approach, other is known as the top-down approach. In the bottom-up approach, we will be putting together, you can say the atoms or molecules. Basically, we will be putting the atoms. So we will be having the new nanostructures. So in the top-down approach, one will be starting with the larger structures, larger materials, which are known as the bulk materials, and reducing the size of the bulk material step by step to produce the nanoparticles. In most of the cases, when we have to fabricate the nanomaterials, good quality nanomaterials, we will be using the bottom-up approach. Because the nanomaterials grown by the bottom-up approach are free from defects. In case of the top-down approach, the synthesized material will be having many defects. In case of the bottom approach, we are having the ease of doping in the grown nanostructures. In case of the top approach, we will not be having that ease. The purity of the structures grown by the bottom up will be very good, but by the top down, that purity chances of the purity introduction will be there. So well-known bottom up and the top down techniques, which are frequently used, are the mentioned here in this slide. So frequently used bottom-up techniques are colloidal chemical precipitation, sol-gel method, template synthesis, hydrothermal, solvothermal, gas phase condensation. Similarly, commonly used top-down techniques are lithography, reactive etching, wall milling. So in my laboratory, we are using mostly on the bottom-up synthesis techniques. So nanomaterials can be very easily synthesized using method. The morphology control over the materials morphology will be very less of the chemical, but for the general purposes, you can easily synthesize the nanomaterials for the general application by using the chemical precipitation. So if you have to, for example, synthesize cadmium sulfide, if you have to synthesize, for example, zinc sulfide or the doped cadmium zinc sulfide, you can easily mix the precursors of these materials under the controlled conditions. You can have the formation of the required material. So it has been seen that when we are fabricating the nanomaterials, so due to high surface to volume ratio, due to high surface energy, there may be the chances of the agglomeration. The size will go on increasing. So to control that size increase, size growth, we will be using the capping agents. So in my laboratory, we have synthesized approximately 1,000 type of the different materials. So we are commonly using chemical co-precipitation, hydrothermal, solvothermal methods, sonochemical, sol-gel refluxing, solid state reactions, green chemistry routes, biological methods, template synthesis, ball milling, etc. Until now, we have synthesized many type of the ceramic and the chalcogenide semiconductor nanostructures, as well as the carbon nanostructures and metal nanostructures. So basically, I was saying that it is a problem with the nanomaterials that self-assembly of the nanostructure is taking place. Self-assembly is very helpful for the biological growth because our biological growth is taking place by self-assembly. But in the synthesis, in case of synthetic materials, sometimes self-assembly will be causing problem for us when the size will be growing beyond the required size. So to control, you can say, the size growth, we will be using the capping agents. We will be capping the material. So that capping agent will be causing the electrostatic forces that will be sterically hindering the, you can say, grown particles and will be not permitting the further growth. Basically, nanoparticles are not stable due to falling three regions. Self-assembly is responsible for the instability of the nanoparticles. agglomeration due to high surface energy can take place, or the osterwald ripening using the capping agents, or we will be using these materials in the templates. So there are so many techniques. Basically, for the general purposes, for example, we have to use nanomaterials in the cosmetics, we have to use nanomaterials in the paints, in the coatings. So large size variation can be allowed. But when we have to fabricate the devices, for example, we are interested to fabricate the quantum dot-based lasers. We are interested to fabricate the nanosensors. In that case, size variation should not be large. So when the size variation is very narrow, so we are saying that those nanostructures are having high monodispersity. So we require monodispersed nanoparticles for the fabrication of the devices. So it is a very hot topic in the nano researches that how monodispersed nanostructures can be fabricated. So to synthesize the monodispersed nanostructures, two techniques are commonly used. One is known as the direct growth, in which we are using the template synthesis. In a template, researchers are growing the nanoparticles. Second is the self-assembled growth. For example, epitaxy. Epitaxial technique, molecular beam epitaxy is a very good technique to synthesize the nanostructures with a narrow side distribution for the device applications. MOCVD, metal organic chemical vapor diffusion, is also another good technique to synthesize the highly monodispersed particles for the device applications. So after the synthesis, we have to go for the characterization. So preliminary characterizations are the nanosize formation confirmation, crystallographic characterization, morphological and topographical characterization, quantitative and qualitative analysis. So these are the few preliminary characterizations. After these characterizations, we can go for the field-specific characterizations. For example, if we have to use the material in the automobile sector, we can go for the mechanical strength. If we have to use the material for the magnetic application, we can characterize the magnetic characters, thermal properties. So there are so many other properties, other characterization techniques, but these are the preliminary characterization. So nanosize formation confirmation. For example, we have synthesized an unknown powder. So is that powder the required material? Is that powder has the nanosize particles? So first of all, it is the requirement of the synthesis that you have to confirm the nanosize formation. So after that, we will be going for the crystallographic characterization. So when we are fabricating the nanomaterials, most of the nanomaterials are crystalline in nature. So to confirm the nanosize formation in those materials, we can use the diffraction techniques. Commonly used diffraction techniques are X-ray diffraction. In some cases, electron diffraction is used, and in some other cases, neutron diffraction is also used. X-ray diffraction is a very beautiful technique, but the drawback of this technique is that here the diffraction intensity depends upon the atomic number. So for the low Z elements, for low atomic number elements, sometimes diffraction intensity is low. So due to that reason, this technique fails. We have to use other techniques, electron diffraction or neutron diffraction. So in case of the electron diffraction, diffraction intensity don't depend upon the atomic number. Neutron diffraction is having another beauty that along with the crystallographic characterization, along with the nanosize formation, you can also characterize the magnetic properties of the material. So from the diffraction techniques, in case of the crystalline materials, we will be having the information about the nanosize formation, nanosize crystallite formation, and we will also be having the other crystallographic characteristics information from the recorded pattern. So this is this diffractogram was recorded for bulk zinc oxide as well as nano zinc oxide. So from the comparison of these two patterns, so this is for the bulk zinc oxide, this is for the nano zinc oxide. So it has been seen that when the size will be go on reducing, the peak will be go on broadening. Diffraction intensity will be go on decreasing. So if the peaks, diffraction peaks are lying at specific positions at specific diffraction angles, but if the peak width is go on increasing, so we can say that the nano-sized crystallites are formed in the material. This peak broadening can be due to other regions also. There are the two other regions. One is the strain. If the strain will be present in the system, present in the material, the peak broadening can take place. If the error in the instrument, if the diffractometer is not properly calibrated, so the broadening can be take place. But otherwise, if other two parameters, strain and calibration, is not having any problem, so the peak will be confirming that nano size has been formed. So from the recorded pattern, for case of the spherical particles, average crystallite size can be calculated using this formula. This is known as curve formula. So in this formula, average crystallite size will be equal to 0.89 lambda beta cos theta. Here lambda is the X-ray wavelength. Beta is the full width half maximum of the peak. Theta is the diffraction angle. So it is the beauty of the nanomaterials that every property will be becoming site tunable on nanoscale. So here, this is the diffraction pattern which was recorded for cadmium sulfide. So it has been seen that in this case, the structure of the cadmium sulfide was zinc blende and the average crystalline size was 3 nanometer. We have recorded the diffraction pattern for different sized nanoparticles of the cadmium sulfide. So it has been seen that when the size was go on reducing from 7.5 nanometer to 5.5 nanometer, so the broadening in the XRD pattern was go on increasing. So with the decrease in the particle size, what will be happening? The peak broadening will be taking place. Similarly, it has been seen that it is the beauty of the nanomaterials that the crystal structure will also be changing. In case of the cadmium sulfide, when the particle size was approximately 25 nanometer, the crystal structure was burzite, crystal structure was hexagonal. But when the size was reduced to 11 nanometer, it was having a mixture of the cubic zinc blende as well as the burzite structure, hexagonal structure. But when we were reducing the particle size, it was becoming the zinc blende. So here we can see that basically with the decrease in the particle size, the crystal structure will also be changing. Because the surface to volume ratio is increasing, large number of the atoms are coming on the surface energy is increasing, instability is, you can say, coming into play. So to achieve the more stability, the structure will be becoming more compact. So due to that reason, it has been seen that the hexagonal structure was changing to the cubic structure. So if we will be going to the atomic cluster scale, further this structure will also change. So you can say that nothing is fixed, everything will be depending upon the size. So similarly, with the annealing, crystallography will be changing. So after the crystallographic characterization and the nano size formation confirmation, we have to go for the morphological characterization. Morphology, I have told you that basically morphology is size and shape. So here we cannot use the conventional optical microscopes because the conventional optical microscopes, due to diffraction limited vision, cannot see the nanoparticles, nanostructures. So we have to use here other type of the microscopes. So commonly used microscopes here are electron microscopes, scanning electron microscope and transmission electron microscope. These are two base models of electron microscopes which are used to visualize the nanomaterials. Other type of the microscopes are scanning probe microscopes. In this family, there are two common names: scanning tunneling microscope and atomic force microscope. These microscopes are also used to visualize the nanomaterials as well as to manipulate the nanomaterials. So sometimes to visualize the bigger structures, confocal optical microscope is also used. So in the confocal optical microscope, we will not be going in detail. In the confocal optical microscope, basically, it is the fluorescence-based technology, and we can visualize the bigger side nanostructures. So basically, in the electron microscope, we are using electron beam instead of the optical signal, instead of the light beam. So only difference in the electron microscope is that we are replacing the optical light beam which was used in the optical microscope with the electron beam. So the optical components will also change because when the beam will be changing. So in case of the scanning electron microscope, we will be using electron beam and that will be scanning the surface of the material. And in case of the electron microscope, the electron beam will be transmitting through the sample, thin sample, and the pattern will be recorded. But the beautiful microscopes are the scanning probe microscopes. As I have told you that with the invention of the scanning tunneling microscope in 1985 and with the invention of the atomic force microscope in 1985, thereby the revolution in nanotechnology. So we shall discuss a little bit about these microscopes. But if we have to compare the various conventional microscopes with the scanning probe microscopes, so it has been seen that magnification of the optical microscopes is of the order of thousands, 10 to the power 3, 14x, 1400x. Confocal microscope is having magnification 10 times more than the optical microscope. So its magnification is of the order of 10 to the power 4x. Electron microscopes are having magnification 1000 times more than the confocal, and the magnification of electron microscopes is of the order of 10 to the power 7x. But scanning probe microscopes are having very, very high magnification. Till date, those are having a magnification of the order of 10 to the power 9x. So in the scanning probe microscope, basically we will be having a tip of that probe will so that probe tip will be moving on the sample surface, very near to the sample surface. The separation between the tip and the sample surface will be only few nanometers. When it will be near to the sample surface, so the tunneling of the electrons will be taking place between the tip atom and the surface atom. So we will be measuring a tunneling current. So by measuring that tunneling current, we will be knowing about the nanomaterials. Morphology is important. There is another term which is known as the topography. Basically, topography is related to the surface features. So the surface roughness, surface features, all these are coming in the topography. So with the help of the scanning probe microscopes, we can know about the topography as well as the morphology. So basically, our tip will be scanning on the surface. So here we can have the two common modes. One is the known as constant height mode, other is known as the constant current mode. Means we can fix the tip at constant height, that will be moving at the constant height, and then the current will be changing, tunneling current will be changing. That can be measured. Or in other case, the constant current mode, current will be remaining fixed and the height will be changing. By monitoring these changes, we can know about the morphology and topography of the sample. So this picture is telling us about the principle of the operation of a ST. So this is the STM micrograph of graphite HOPG. So here in this pattern, we can easily see the atoms. So these black dots are the atoms of the carbon. Similar in atomic force microscope, what will be happening? We will be having a cantilever, sharp tip cantilever. That tip will be coming close to the surface of the sample. So basically here, we will be measuring the forces of attraction and repulsion which will be taking place between the tip and the surface atoms. Those will be measured. So due to this region, it is known as the atomic force microscope. So this is the block diagram of the schematic of the atomic force microscope. We will not be going in detail about these microscopes. These are a few electron micrographs recorded in my laboratory. So you can synthesize any type of the structure, raw type structure, particle, spherical, cubical, flower type structures can be synthesized. So these are the beautiful 10x nanostructures synthesized in my laboratory. So these are the field emission scanning electron microscope images. As I was telling you that basically the base models in electron microscopes are scanning electron microscope and the transmission electron microscope. But the advanced models are the field emission scanning electron microscope and a high resolution transmission electron microscope, which are having more advancements in comparison to the base model. Today we are also having STEM, scanning transmission electron microscope, which is a combination of both these two instruments. So these are the beautiful structures. So you can see from these micrographs that we can have any type of the structure. We can have the rod type structure. We can have the flower type structure. We can have the spherical particle, cubical particle type of structure. So these are the high resolution transmission electron microscope images along with the select area electron diffraction. So basically in these electron microscopes, along with the electron micrographs, we can also have the information about the crystallography of the sample. We can also have the information about the quality of the sample. So when we have to talk about the crystallography of sample, we will be recording the electron diffraction pattern. So here SAED is the select area electron diffraction. So this is a select area electron diffraction pattern. From this pattern, we can also know about the crystallinity of the material. So here, if we will be having a dot pattern, so sample will be single crystalline. If we will be having the well-defined ring pattern, sample will be polycrystalline. If we will be having a diffused halos, sample will be amorphous. Similarly, as in physics, as well as in chemistry, we are talking about the defects or the dislocation in the materials. So with the help of electron microscopes, we can see the presence of these defects and dislocations. These are the few micrographs, few studies which we have carried in our laboratory. So we were discussing that band gap broadening is taking place on the nanoscale. So we have performed experiment in our with cadmium sulfide. So the band gap of the bulk cadmium sulfide is 2.42 electron volt. But it has been seen that when the size of the nanoparticles was changing from on 30 nanometer to 2 nanometer, so the band gap was go on broadening. So this is the UV visible absorption spectra. So it has been seen that thereby the blue shift in the absorption spectra. So broadening it has been the emission spectra to band broad. That shift in the absorption spectra will be telling us about the reduction in the particle size. So in that way, if you're not having microscopes, synchro microscopes or XRD in your in laboratory, so if you're having a UV visible absorption spectrometer, so from the absorption particles, so using the edge, you can also be changing with the decrease in the particle size. So this was recorded for the particles having size from 25 nanometer and reduced to 2 nanometers. So it has been seen that with the decrease in the particles, it was the blue shift in emission color as well as the emission intensity was going increasing with the decrease in the particle size. So it has been seen that up to 5.5 nanometer size particle with the emission intensity was going. But when we were going beyond that 5.5 nanometer size particle, the emission was a little bit decreasing. So this is due to the reason that with the decrease in the particle size, surface to volume ratio will go on increasing. So up to optimum value, basically the volume defect states will go on decreasing with the decrease in the particle size. So when the volume defect states will go on decreasing, so it has been seen that optical, you can say, properties will be enhanced. But with the further decrease in the particle size, the dominance of the surface defect state will come into play, which may quench the luminescence. So due to that reason, it has been seen that up to 5.5 nanometer size, the luminescence was increasing, but beyond 5.5 nanometer, when we were going to 2 nanometers, so again, the intensity was decreasing. So these are the few steady state luminescence spectra which we have recorded in our laboratory. We will not be going in detail. So it has been seen that with the decrease in the particle size, the luminescent behavior, luminescence color will be changing, and the excited state lifetime will also be changing. So for the display device application, it is the beauty of the nanomaterial that the luminescence intensity is increasing, which is known as the luminescence quantum yield. Emission color is changing. Secondly, if we look on the excited state lifetime, decay time, so it has been seen that with the decrease in the particle size, decay time will also be shortening. So in case of the 25 nanometer size particles, the decay time was 25.41 microsecond, but when we go to 2 nanometer size particle, so this time was becoming only 1.25 microsecond, which is very, very small. So in that way, you can say that by reducing the particle size on nanometer scale, we can synthesize fast and efficient phosphor materials for display application, display device applications. So these are some other results. We will not be going in detail. So in our laboratory, we are also performing the photocatalytic studies. So nanomaterials are very good photocatalysts. So these are usually either heterogeneous catalysts for the purification of the contaminated water. So when we will be exposing the nanomaterials to the radiation, so the material will be excited. Basically, here we will be using semiconductor materials. So after excitation, electron hole pairs will be generated. So when those electron and holes will be participating in the oxidation and the reduction reactions in the solution, so those can purify the contaminated water. So in our laboratory, we have performed these experiments. We have used methylene blue dye mostly as the test contaminant in our laboratory. Sometimes we have used also the other rhodamine dye also. So it has been seen that the water was purified in our laboratory. It has been seen that the photocatalytic activity also be depending upon the particle size. So it has been seen that when the particle size was reduced between 30 nanometer to 2 nanometer, it has been seen that the photocatalytic activity was go on increasing with the decrease in particle size up to this size. But when we go further beyond this 5.5 nanometer size to 2 emission, again here it has been seen that the photocatalytic activity was also decreasing. So here you can conclude that there is a critical size for every property. If we will be going beyond that critical size, so that property will not be having more smartness. So with the decrease in the particle size, catalytic activity, photocatalytic activity was enhancing up to the critical size. Why it is so? Because the rate of the volume charge carrier combination decreases with the decrease in the particle size. But if we will be going beyond critical size due to the enhanced surface to volume ratio, rate of the surface charge carrier combination increases below critical size. So to that reason, it has been seen that the photocatalytic activity will not be so good below the critical size. Similarly, in our laboratory, we are fabricating the nanosensors. We are also working on the photovoltaic cells, but we will not be going in detail. But it has been seen that these nanomaterials are very good nanosensors. So in the end, in the few minutes, I will be a little bit talking about the applications. So it has been seen that nanomaterials are having very, very smart applications. Tomorrow, we will be needing no washing machines. We will not be needing no regular use of the medicine. So basically, these ideas are coming from nature. So it has been seen that we will be having the smart textile. We will be having, you can say, flexible electronic sticks. We will be having the nano bandages, man-made skin. I am not going in detail because tomorrow you will be having a special lecture on the application, but I am giving a little bit idea about the application of nanotechnology. So we are having the application of the nanomaterials in refrigerator, in the washing machines. So nanomaterials coated inside the refrigerator, the washing machines are killing the bacteria to take the things fresh. So carbon nanotubes are used in the batteries. So nanomaterials are used for the fabrication of the fast and efficient nanophosphors for displays. So these materials can give us the quantum computers, which will be, you can say, very, very fast in comparison to the existing computers. Those will be having very small size. People are talking about the molecular computers also. So it has been seen that nanotechnology will be affecting every aspect of our life. We will be having the nanomaterial-based displays of our gadgets. We will be having the photovoltaic films on the glass windows. We will be having a scratch-proof coated windows. We will be having the smart textile. We will be having the, you can say, composite-based our furniture items. So everywhere nanotechnology will be playing very important role. Nanotechnology will also be very, very helpful in the medical sector, for improving diagnosis, for improving imaging. So it will be giving us the new ways to treat diseases. It will be helpful for the superior implants. Even the nanotechnology will be helpful to remove the, you can say, harmful bacteria from teeth. Nanorobots will be helpful to remove the fats from the arteries. So it has been seen that the biological memory will be very, very helpful in the electronics. So in India, DRDO is performing the special type of the research and development activities in the field of the nanotechnology. So DRDO scientists are working on the gas sensors, IR reflecting coatings, materials for thermal insulation, low emissivity films and coatings, magnetic nanoparticles, nanomagnetic materials, nanocomposites. So means DRDO, other CSA labs in India, along with the thousands of researchers around the globe are working on the nanomaterials. So in army, researchers have inside a composite of zinc and carbon. that composite can produce the heat, self heat by electrochemical oxidation. That type of heater, self heater, heat producing heater is used for the heating, or you can say, of the meal in the battlefield. Smart uniforms are, for the soldiers are also fabricated. Nano applications in the food are very, very huge. So nano packaging materials are used. So people are working in the simulation, also in the theoretical nanotechnology. People are talking about the fabrication of the nano machines. So it has been seen that with the nanotechnology, we will be having peace, because we will not be having any problem. We will not be having any health problem or any food grain problem. So we will be having free from pollution, but it is only possible if we will be having the nanotechnology in the safe hands. So future challenges of nanotechnology, the areas in which someone can work. So we have to design, we have to search for the new design techniques for the fabrication of the nanostructured materials. You can work in the nanoelectronics, optoelectronics, and magnetics, advanced healthcare, nanoscale processes for environmental improvement, efficient energy conversion and storage, microcraft space applications, bio-nanosensors for biological threat detection, application to economical and safe transportation, application of nanotechnology. There are so many applications in every field. So in conclusion, I can say no one knows how much of nanotechnology's promise will prove out. Technology prediction has never been too reliable, but there is plenty of room at the bottom. Thank you. Thanks for attention.
Singh, for sparing your time. I feel very proud that I am your student in MSc, and again I get a chance to learn something very valuable from you. It was very fruitful and informative lecture for all of us. Now I request all the participants to share their videos so that we can take pictures. I request all the participants to share their videos so that we can take photograph.
And share your screen.
Yeah.
Can you hear me, Dr. Bhamri?
Yes, sir.
I'm on behalf of A.S. College Khanna and Department of Physics. I am thankful to Dr. Karamjit Singh Dhaliwal, who has spared all the time, and definitely our students will be benefited, because these days I think this is one of the most relevant topics. So nanotechnology and use of relevance of nano elements, I think it definitely is the talk of the day now. So I think it's the use of this nanotechnology is most of the relevant now these days. So once again, I am thankful, Dr. Karamjit, for sparing time for our students, and I think definitely students and the faculty will be benefited. Thank you very much on behalf of A.S. College Khanna. Thank you, sir.
Thank you, sir. Thank you. Welcome.
Thank you so much, sir. I also thanks to Dr. Vivek Pambriji for their technical support, and I also thanks to faculty member of Physics Department. Once again, thank you so much. Thanks a lot.